Hello and welcome back to STEM Online Academy. My name is Jason Masterakos. For those of you who don't know and who are potential viewers slash subscribers, for those of you who do know me, you know what my channel is about. Uh, STEM Online Academy is a YouTube channel that is to help undergraduates, mainly undergraduates. We also help, researchers too, but mainly undergraduates uh, who in advanced mathematics and physics to help cultivate uh, their mathematical maturity, okay? Or should I say mathematical intuition, strengthening their mathematical intuition, right? Uh, Lots of you understand what I mean by that, right? What that means is that a sixth sense when it comes to doing math problems or understanding math concepts. All that is just gaining an understanding of how to tackle any type of problem, regardless of how easy or how difficult it is. And that comes through lots of practice, through hard problems. Okay. So, those of you who know me and the channel, right, that's what I'm all about, right, is to uh, help you, the viewer, the undergraduate, I assume, get much stronger through uh, challenging concepts and problems that will hopefully develop your mathematical intuition. Okay. So today is going to be a stream day, as you already know. Okay. I do twice a week is streaming, right? And once a week is the live show. Okay. So that is pretty much the schedule now, right? At the end of the video, I'll discuss exactly in more detail when and what times you can look out for the streams and also for the live show. Obviously, the live show is the most fun, okay? Because I get to interact with you guys and we get to go through problems in a lot of detail, whatever those problems may be. All right, so let's get back to it. Um, so I've already made. You're probably looking at the title and saying Residue Calculus Masterclass. Probably thinking I already made an episode on the residue calculus. Right? I believe it was a live show we were discussing the theorems on that. Um, so if you haven't seen, for those of you who are really just wanting to learn residue calculus, but you don't know any of the definitions or theorems, please refer to the other episode. This should be on my YouTube channel. It's one of the live shows and says something about complex analysis. I go through some problems in the book. But before doing that, I go through the theory in detail. Right? I spend a lot of time in the theory. Make sure you understand the theory first, and then if not, come to this. All right. So that's for one aspect of the audience. The other aspect of the audience is for viewers who already, you already know the theorems, definitions, and stuff like that, but you still conceptually are struggling and you need a guide, right? So this is going to be for you. Okay. So we're going to look at the residue calculus contour integration today. All right. So that's what I thought would be the next thing from my book that we're going to be discussing. All right. Residue calculus is very fun. So let's get to it. All right. So, in this master class, we're going to be looking at exploring the residue theorem. Okay. Pretty much, this is the most elegant tool in complex analysis. Okay. And let me just go down here to explain in more detail. Okay. So, why residues matter. Okay. So that's first thing on today's menu. Two, poles, residues, singular behavior. Three, uh, our first contour integral, right? Four, upper and lower half plane sections. Five, real integrals using residues. Six, infinite sum evaluation. And seven, summary and advanced applications. Don't worry, this will not drag out very long because I'm not going to be solving problems in this video, in the stream. I'm going to go through common misconceptions that people have when it comes to contour integration. Okay, that's going to incorporate all of these. some in more detail than others. Okay, so why do residues matter? Okay, well, we do have a theorem, right? Just to remind those of you, the residue theorem. Okay, let me just put this up here for now. Okay, so let me just, so residue, so I'm going to put DEFN, so DEFN, just to remind you one definition or theorem here. I'll just say theorem. It's better with that. I use blue. Theorem. Okay, and it's the residue theorem, right? The residue theorem, right, states if you have multiple residues, right, in your contour, non-singular. Let me repeat, non-singular. Okay, so if you have non-singular, so let me put down here, when you have multiple non-singular, just going to repeat one theorem, right? Only in this lecture, as I mentioned, non-singular, singular. When you have multiple non-singular poles, right? Poles in your contour called C, put over here, contour C. Okay, we add up, so we have to add up all of our residues. Okay, and our residues are the following below, right? So it states that, let me use a different color here. I use blue now. Yeah, so our integral, our contour integral, it's a loop integral, right? Of f of z dz. Z is a complex number, is equal to the sum from k equals 1 to n of the residue of f of, let's say f is a function of z sub k, f a function of z sub k, comma, z sub k. Okay, so this is just the sum of all the residues at the poles that were non-singular. That means they're within the contour that we're dealing with. I'm going to explain in more detail, conceptually, with visuals. Okay. All right, so let's do that right now. All right, so let's look at a visual here. What type of visual will be the handiest? So we're going to start off. Okay, so we're going to start off with, let me see. Well, this is one of the reasons why residues matter. Okay, residues matter because they turn global integrals into local data. Okay, that's the way you have to understand residues, right? Instead of just integrating along a complicated path, we only need to understand what happens near the singularities. As I said, the most important thing, at least one of the most important things when it comes to contour integration and all of that stuff, right, is to make sure you understand what's happening with the singularities. Okay, so if you're not understanding what I'm saying, refer to your lecture notes from your courses or go to my channel and look up the definitions and theorems. The live show I had it, I was talking about that, okay, about contour integration, definitions, theorems. All right. Now, what I want to do is I want to fix a misconception. Okay, and one of the main misconceptions when it comes to the contour integrals is that students think contour integration is about, you have a fancy path, and that's the only time you use it is when you have fancy geometric paths. Okay, this cannot be further from the truth. Okay, that's not true. We don't use it just when we have fancy paths. Okay, it's actually about local behavior near the poles. I keep emphasizing the behavior around the poles of the contour, right? Those non-singular parts of the contour are the most important aspect of contour integration. Okay, so I'm gonna show you right here. Actually, let me go to my desktop. Okay, so let's go to the desktop. I'm gonna show you a simulation. Okay, just 1 second. So we're gonna look at. Give me a sec here. One of these simulations. Okay. Actually, before doing that, let's get back to the desk. Let's go back here, right? All right. So yeah, just before getting to the simulation, I want to also talk about poles, residues, and singular behavior, just to remind yourselves, even though I'm not putting down a definition. Okay. So what is a pole? A pole is where a function blows up in a controlled way. Okay. And the residue is the coefficient of the 1 all over z minus z0 that you guys are used to, right? Like that 1 over z minus a. It doesn't matter what we call it, z0, a. It all means the same thing, right? The term, the z minus z0 term, right? So it measures how much the function leaks into the integral, okay? That's what it does. That's what poles do. It measures how much the function leaks into the integral. So think of it as almost as an analogy of a fluid leaking into something, okay? That's what this thing measures. Right? That's what poles measure. Now, another misconception that students have, right, is that they confuse poles with zeros or think of all singularities behaving the same. Okay, so poles are not zeros that you're used to like in your grade 10, 11 math classes. That's not what we're talking about. Okay? That's not what we're talking about at all. Let me show you the simulation now. Okay, so if you go here, we're gonna look at our first simulation. Is this the right one? Yeah, it is. Okay, so let me just rewind. Okay, so here we have a simple pole, a common one. F of z is equal to 1 all over z minus a. Okay, and what we're getting here, right, is you get something interesting. What do you notice with that 1 over z minus a? Well, look, if you look at it again, right, so we have a pole on our real axis and imaginary axis. And then we have a line pointing to the pole. The pole, by the way, is that just that dot there, but that line is pointing directly at the pole. All right. So that 1 all over z minus a, exactly what it says there. We're isolating a singular part of that expression there. Okay. That's all it's doing. Right. So that 1 all over z minus a, we're just isolating the singular part. The singular part is in the z minus a. Okay. This has nothing to do with restrictions, because if you had a restriction or a zero, it would have been an asymptote. We're not talking about that. A pole is a dot, geometrically a dot on the real and imaginary axis, right? Where we've isolated the singular part, the singularity there, right? The 1 over z minus a. Okay, that's all it is. All right. So looking at that, right? And if that was in the real and imaginary axis, if you look at the other real and imaginary axis, one for the z plane, one for the w plane, you can see that not only the pole has a line pointing to it, because remember, real and imaginary axis, the coordinates of that pole is just a vector, right? So geometrically, it creates some sort of vector there, right? So from the z plane is also showing a vector, right? The line's going to the left all the way to that pole, hitting the pole there. And the w plane, we have a line going from left to right. It's also going to be some sort of a pole. Okay. All right. So I hope that clarifies things. All right. So we can stop with this guy here. Let's get rid of that. Go back to the desktop. Okay. So I hope that clarifies the difference between what a singularity is compared to what zeros are. Right? Like I hope it clarified the misconception. Okay. All right. So let's look at a contour integral. Okay. And when I mean looking at a contour integral, right, I mean conceptually looking at the contour integral. Okay. All right. That's what we're going to be doing. right? So when it comes to contour intervals, right, you have to make sure that you understand a few things, okay? When you integrate, right, so this guy over here, and a lot of you know this, you at least started to see contour integration for the first time or whatever, is that when you integrate 1 all over z minus a around a loop, right, that's what this is, it's a loop interval, around a loop enclosing a, you aren't going to get 0. You get 2 pi I. Okay, that's where this, by the way, I made a mistake here. There's supposed to be a 2 pi I right in front of my sum. Okay, 2 pi I times the summation. You get 2 pi I. That number is purely geometric. Okay, so why am I bringing this up? Because quite often students think that complex intervals should behave like real ones. They don't. The way we integrate in the complex space is not the same the way we integrate in the real space, like with real numbers. Complex numbers and real numbers, the way we integrate for reals is not the same way we integrate for complex. Okay, I'm going to repeat. The way we integrate on the reals, right, is not the same way that we integrate for the complex numbers. Okay, so let me show you a really cool simulation if you want. All right, so let's go. I hope you guys are enjoying the simulations. Okay, because the whole point to this is I'm trying to show you guys in a geometric fashion how to understand math, right? Not just me always solving equations. So let's look at this one right here, right? So we have a contour circling a pole with 2 pi I, right? And what you can see with the pole, right, is right at the location 0, comma 0, okay, at those coordinates on the real and imaginary axis. And our contour is this circle that's going a circle with a yellow dot following a trajectory that's going in a counterclockwise rotation, okay? That's what's going on here, all right? So what's going on here, again, I repeat, we have a pole located at 0, comma 0, those coordinates, on the real and imaginary axis, right, on the complex plane, okay? And the contour is a full circle, okay? On that full circle is this yellow light, and that yellow light goes in the counterclockwise rotation, okay? As you can see in the simulation here, it's moving a counterclockwise rotation in a really fancy type of way. Okay. Now, at the same time, right, right, this circle, this contour that we have, has some interesting parameters here. Actually, if you look at it, okay, we have a loop angle, okay, and we also have a counter, okay. The counter is dependent on the imaginary number I, okay. It's not as important. That's not the main point of this, all right. Full loop. Well, the full loop hopefully explains why we have to multiply our sum of all of our residues by 2 pi I, right? Because the entire full loop is 2 pi radians. That's why we always multiply it by 2 pi. For those of you who didn't understand why they have the 2 pi I in front of the summation, okay, that's why we have it. All right. And as you can see, that our contour is circling a pole, again, with a counter ticking up to 2 pi I, right? As the loop closes, right? That's the whole point of this here, okay? So I hope that explains as to why for the contour circling a pole with a 2 pi I counter, okay? Hopefully that explains why when we integrate on the reals, it's not the same as integrating in the complex numbers, right? Because for complex numbers, we have this circular loop and we have to sum up by a constant of 2 pi I, okay? All right, so that's simulation T. Let's go back. Okay, so what we're going to be looking at next, right? So we looked at why residues matter. Okay, we've talked about this. Poles, residues, singular behavior, our first contour interval, we've talked about it. At least we talked about it from a geometric understanding. Okay. All right. I think we'll look at the upper and lower half plane sections. Okay. I think we should do that next. All right. So upper and lower half plane sections. So let's talk about that next. So when it comes to upper and lower half plane sections, okay, I want you guys to make sure that you understand what I mean by that. All I'm saying is you don't just choose the contours arbitrarily, right? You don't choose contours arbitrarily. You never do that. You choose the half plane where the exponential will start to decay, okay? And pretty much when you do that, the growth is going to kill the integral, but the decay will save them. Let me explain what I mean by that on the next simulation. Okay, let's go here. Just give me a moment. Just give me a sec here. And there's a reason why I want to go to the simulation. This is a very important one. Okay, is because quite often students memorize the upper versus a lower half of the plane rules without knowing why. This is a common misconception. Actually, I'm going to label something here. I'm going to write something down. I'm only going to write if I actually need to write. Otherwise, I'm just mimicking what I've written. If you have a plane or a Cartesian, any type of plane, doesn't matter. Let's see, you have the real and imaginary axis. The real axis and the imaginary axis. Okay. And let's say you have a contour. Well, I'll get to it in a second. Let's say you had to integrate something like this, integral of dx over x squared plus 1. Okay, you can use contour integration to do this. Quite often people will integrate this and they'll say, oh, wait, if I use contour integration, I need to create a semicircle, upper half plane of the semicircle or lower half plane. Okay. Now, that's good and all, but people don't understand why they're doing that. They don't understand why they have to create a semicircle. And that's the biggest issue here, right? Okay. Yeah. Okay. Whatever. You're creating a some sort of semicircle for any type of integral in the form of x squared plus a squared. However, though, they don't know why, though. They don't know why they're doing it. And quite often, maybe it has a going counterclockwise rotation. This is C, whatever. Okay. I'm here to fix that fact. What you have to do is, okay, so I'm going to explain why. Okay, so simulation 3. Okay. So when I was talking about growth and decay, this is a very important thing here. Okay, so if you have a growth amplitude, exploding amplitude, and decaying amplitude, in other words, obviously decay, one is showing exponential growth, one is showing exponential decay. Okay. Now, based off if it's exponential growth or exponential decay, you have to choose your contour wisely. Okay. Based on the trajectory of the contour, right? So what I mean by that is exactly what it says here at the bottom of my simulation that I made. Okay. Pay attention. Think of moving in opposite imaginary directions, right? One side makes, let's say another example, e to the I z. That's another integral that's common that you may be asked to integrate. Okay. So if you had e to the I z, just wait for it again. If you have e to the I z, it will blow up, right? The other makes it decay. Okay. So when it comes to doing contour integration, right? Especially when you have to integrate something like x squared, dx over x squared plus 1 or something like that. Yeah, it can be, people are like, okay, I know that the upper versus lower half plane rules uh, is what I'm going to use for integrating something in the form of dx over x squared plus a squared, right? But they don't know why though, right? So by showing you the simulation here, okay, right? The left one showing e to the I z exploding upward, and the right showing e to the iz decaying downwards, okay, uh, you can see the decay, right? So hopefully, right, based off of these, one is showing the upper part, right? So if you had to choose the lower half of the contour, that's what I'm saying, right? Think of this as being the lower half of the contour, both these parts, the left exploding amplitude and the right decaying amplitudes from their different paths there. Just the lower half, one half of the lower half and one half of the other lower half. That gives you a reason why you have to choose the upper or lower based off of this. I'm just partitioning the lower half of the semicircle. Okay. So I hope that is making more sense. Okay, so let me just go back to the desktop. Okay, so back to the desktop. Okay, so then with the upper and lower halves, real integrals using residues. Okay, I think we should talk about real integrals using residues. Okay, so yes, you can use complex integration for evaluating advanced uh, real integrals that couldn't be solved otherwise. Okay, but what do I mean by that exactly? Real integrals just become complex integrals in reality. That's what they are. They're complex integrals. Okay. When the symmetry and decay lets us close the contour, right? Then the residue theorem does the rest. As I mentioned, this guy right here. This needs to be read and butter. This is the most important theorem in contour integration. Okay. So make sure you understand it, right? Right. Real integrals become complex integrals when symmetry and decay let us close the contour. Okay. Now, what's a common misconception here that a lot of people have? Okay. Students don't see why complex methods apply to real integrals. They just don't see it. Let me show you why this is the case. Okay. All right. So we've done G3. Yes, we're going to be looking at the real axis lifting into a closed contour. Okay, so here's a real axis and how it becomes a closed contour when you have real integrals plus residues. Okay, so as you can see here, here's my contour. Okay, and it's going in the counterclockwise rotation along the upper part of a semicircle with non-singular poles, right? When I mean non-singular poles, I mean the residue 1 on the left part of the semicircle, residue 2 on the right part of the semicircle. Okay, if you understand what I mean. So again, we have a very interesting contour that we're doing. This is the most common contour that we use is the semicircle. It's not always used though, but yes, right? So by having the real axis and then having the closed contour, okay, this implies that we get real integrals plus residues, okay? And as I said, right, that's the residue theorem, right? The integral over CF of z dz is 2 pi I times the sum of all residues. Right? So in this case, I had residue 1 and residue 2 in my simulation. Those are the two non-singular poles that we have there. And you only take the non-singular poles and sum them up times 2 pi I. Okay? Right? So I hope this explains why real integrals can be computed by using complex methods. Okay? Right, so let's go back to the desktop. Okay, so desktop. Okay. And next thing we're going to look at, that one, infinite sum evaluation. Okay, so what do I mean by an infinite sum evaluation? I know I didn't write it down, but for infinite sum evaluations, okay, I just want to mention that residues don't just compute the integrals. Okay, no, they don't. A lot of times people think residues are only for integrals. Real, complex, doesn't matter what you call it. No, they're for sums too. They're for computing infinite sums. Infinite series actually are hidden contour integrals. Okay. Yes, this is true. Infinite series are actually hidden contour integrals. Now, a common misconception is that students think that residue calculus is only for integrals, as I mentioned. And this is not true at all. Okay. I'm going to show you how poles at the integers, right, uh, light up one by one by then collapsing them into an actual closed sum. Let me do this quickly. Okay, so let's look at our simulation here. So we have, is that the right one? No, that's not the right one. Mistake. We did that one. Let's look at this one here. So here we have poles at the integers. This is a closed form sum. Okay. Now, if you had a sum to deal with and you use contour integration, then you're going to have these poles at multiple integers, as opposed to having an entire contour path. So multiple integers there. Okay. All right. So poles at the integers will imply closed form sums. This is very true. Okay. So seeing the simulation, right? We sum over the residues at the integer poles. That's all I'm saying. Okay, so we're summing over the residue integers at the poles, and you get a closed form sum. For instance, sum of the residue of a Riemann sum, that was a Riemann sum of 1 over ns, n to the s power is equal to pi squared over 6. That's a classic example of a closed form sum using contour integration. Okay, pretty cool. So I hope that clarifies things here when it comes to contour integration. Okay, so let's get out of that. Okay. So back here, and we're practically done. We can probably discuss, sum up everything that we've discussed today. Okay. All right. So after looking at all this, okay, contour integration is not magic. It's bookkeeping. It's tracking the singularity, right? Choosing decays and collecting the residue points, right? That's all it is. All right. Because I know a lot of students feel contour integration is mystical and arbitrary, but hopefully through uh, more of a simulation type of analysis and mathematical modeling, hopefully I've closed a lot of your misconceptions when it comes to contour integration. Okay, right? So if contour integration ever felt like memorizing tricks instead of understanding the math, right? That's exactly why I wrote Advanced Integration Techniques, right? My book doesn't give you shortcuts, but it gives you immense control and immense understanding of why you're doing it the way you're doing it. Okay. So every idea in tonight's video, whether it's residues, decay, real integrals, infinite sums, it's built step by step so you can actually think like an expert, right? Think like a mathematician, or at least an applied mathematician, to be more accurate in this case. Okay. So again, right? My whole concept of the channel is to make you understand, right? Not to memorize. Okay. And or if you want tutoring in areas like this, right? If you want to understand integral calculus in a much uh, deeper conceptual way at a higher level, you can always reach out to me for tutoring lessons. The link, all these links will be in the description below of my YouTube video. Okay. Thanks again to